In this video, we're going to talk about the relationship between noise density and observed noise levels. The observed noise variance in a system is set by how much total noise power the system captures from a noise density spectrum. In other words, systems with wide bandwidths will let in lots of noise variance density, which means we'll see high noise on them, and systems with narrow bandwidths will only let in a little noise variance density, so we'll see low noise variance. You can see this in the shaded area of the spectrum on the right. The noise variance at the output of this amplifier is going to be given by the area under the noise spectrum, and we find that by integrating under the transfer function of our circuit. And just for reference, I've been talking about noise voltage variances on this slide, but this could also apply to noise power variances or noise current variances. We often simplify this calculation by pretending that the bandwidth of our systems is represented by a sharp cutoff, and that's sometimes called a brick wall filter. I've indicated this made-up filter on the transfer function and on our noise transfer function, and on our output noise spectrum. Though this approximation is optimistic if you set your bandwidth wrong, you can get a decent estimate of your total noise variance using this technique. It means that we can replace the integral that used to be in the lower left with just a straight multiplication of our spot noise by the noise bandwidth. We can also rearrange that equation in terms of noise power, and we know our noise power is equal to K times our noise temperature times our bandwidth. By comparing these two equations, we can observe that our noise temperature for this system is A squared times the physical temperature. And that's roughly what we'd expect because the noise temperature just represents a noise variance. It represents the noise power variance. And so we'd expect noise temperature to be scaled by transfer function squared as well. So in summary, the observed noise variance in your system depends on how much noise density makes it through your system's transfer function. We often approximate system transfer functions with brick wall cutoffs to simplify the math. And noise temperature is referred by the transfer function squared, just like other noise variance densities.